The cloud is not invisible. It may feel invisible because we meet it through a screen. A prompt appears. An answer returns. An image is generated. A decision is made. Everything feels clean, weightless, and almost instant. But behind that simple moment is a machine. It has walls. It has power lines. It has cooling systems. It has chips. It has fiber. It has servers arranged in long corridors, pulling electricity through buildings that most people will never see. Artificial intelligence is often described as software. But the deeper story is physical. The AI boom is not only a race to build smarter models. It is a race to build the infrastructure that allows those models to exist. And once you understand that hidden layer, the future of AI starts to look very different. Every AI answer begins somewhere ordinary and physical. A user sends a request. That request travels across networks into a data center. Inside that facility, specialized hardware begins to work. Processors move information at extreme speed. Memory holds the pieces of the computation. Cooling systems fight the heat. Power systems keep the entire chain alive. From the outside, this can feel like magic. But it is not magic. It is computation. It is electricity. It is engineering. It is logistics. It is industrial scale. This is why the AI revolution cannot be understood only by looking at apps, chatbots, or model names. Those are the visible surface. Beneath them is a much larger system: data centers, chips, networks, power grids, cooling loops, supply chains, land, capital, and people building the physical base of intelligence. The first hidden layer is compute. Compute is the raw ability to perform the operations that make modern AI possible. It sounds abstract, but in practice it depends on very real things. It depends on processors. It depends on servers. It depends on memory, networking, and space. It depends on whether enough machines can be built, installed, powered, cooled, and connected. For years, compute was something most people barely thought about. It was background infrastructure. Companies bought servers, rented cloud capacity, and scaled quietly. Then AI changed the meaning of compute. Suddenly, compute became strategic. A company with more compute could train larger systems, test more ideas, run more experiments, and deploy more capable tools. A country with stronger compute infrastructure could support research, industry, defense, science, and automation at a different scale. The race was no longer only about code. It was about capacity. And capacity is physical. That is why chips became central to the story. Modern AI depends on specialized processors that can move and transform enormous amounts of data quickly. These chips are not simple commodities. They sit inside a global supply chain involving design, manufacturing, packaging, memory, equipment, logistics, and export rules. A model may feel like pure software, but its limits are shaped by silicon. If there are not enough chips, growth slows. If memory is limited, performance changes. If manufacturing capacity is constrained, ambition meets reality. If supply chains tighten, the digital future becomes dependent on physical bottlenecks. This is one of the most important patterns in the AI boom. The more advanced the technology becomes, the more it depends on the material world. The second hidden layer is the data center. The Industrial Revolution had factories. The AI revolution has data centers. From the outside, they may look like quiet industrial buildings. But inside, they are becoming the engine rooms of the digital economy. Rows of servers turn electricity into computation. Networks move data between machines. Cooling systems remove heat before it becomes a threat. Engineers monitor reliability, capacity, failures, and performance. The product of this factory is not steel, cars, or textiles. The product is compute. This changes how we should think about data centers. They are not passive storage buildings. In the AI era, they are active production sites. They produce the computational power behind chatbots, recommendation systems, image tools, scientific models, enterprise automation, and future decision systems. They are where abstract intelligence becomes operational. But the data center also reveals a hard truth: AI is not weightless. It needs land. It needs construction. It needs permits. It needs power connections. It needs cooling. It needs cables. It needs maintenance. It needs time. A model can be announced quickly. Infrastructure cannot. That gap between software speed and infrastructure speed may become one of the defining tensions of the next decade. The third hidden layer is energy. Every conversation about AI eventually returns to one simple question: where does the power come from? AI systems do not run on hype. They run on electricity. The more demand grows, the more AI becomes connected to grids, substations, power contracts, energy strategy, and local infrastructure. A data center is not useful if it cannot be powered. A GPU cluster is not useful if heat cannot be controlled. A plan for growth is not real until the physical systems can support it. This is where the story becomes bigger than technology companies. It becomes a story about cities, utilities, regulators, energy markets, construction timelines, and communities. Data centers must connect to the real world. They must fit into grids that already serve homes, hospitals, factories, and businesses. They must manage heat. They must operate reliably. That means the AI boom is also an energy story. Not because energy is a side issue, but because energy is the foundation. Without it, the most advanced model is only an idea. The fourth hidden layer is cooling. Computation produces heat. The more intense the computation, the more important cooling becomes. A data center is not just a room full of machines. It is a controlled environment where temperature, airflow, humidity, and hardware density all matter. Cooling is often invisible in public conversations about AI, but it is essential. Heat can reduce performance. It can shorten hardware life. It can create failure risk. And as systems become more powerful, cooling becomes more complex. This is another example of the physical reality behind AI. The future may be shaped not only by algorithms, but by how efficiently heat can be removed from machines. The fifth hidden layer is networking. AI infrastructure is not only a pile of chips. Those chips must communicate. Servers must move data quickly. Clusters must be connected. Storage must be reachable. Requests must travel across networks and return results fast enough to feel immediate. This requires fiber, switches, routing, software, and physical layouts designed for speed and reliability. When people talk about intelligence, they usually imagine the model itself. But the model depends on a system around it. If data cannot move quickly enough, performance suffers. If networks fail, services fail. If capacity is limited, scale becomes difficult. The intelligence users see is the result of many invisible systems working together. The sixth hidden layer is time. Software can change overnight. Infrastructure usually cannot. A new product can be launched with a press release. A large data center requires planning, construction, hardware, power, cooling, networking, testing, and operations. Chip supply chains cannot be expanded instantly. Grid connections cannot appear by command. Skilled teams cannot be multiplied without training and experience. This is why AI growth can look unstoppable from the outside while still being constrained behind the scenes. The visible race is about models. The hidden race is about bottlenecks. Power can become a bottleneck. Chips can become a bottleneck. Cooling can become a bottleneck. Construction can become a bottleneck. Regulation can become a bottleneck. Networks can become a bottleneck. Even time itself can become a bottleneck. And when a technology depends on so many physical systems, the winners are not always the ones with the best idea. They may be the ones that can execute across the entire stack. That is the deeper pattern behind the AI boom. Artificial intelligence is a software revolution built on an industrial base. It depends on research, but also on manufacturing. It depends on models, but also on power. It depends on algorithms, but also on buildings. It depends on code, but also on copper, silicon, cooling, and concrete. This makes the AI race more complex than it appears. It is not only a race between companies. It is also a race between supply chains, energy systems, infrastructure strategies, and national priorities. It is a race to build the machine behind the machine. The public may see the interface. The real competition is happening underneath it. And this has consequences. If AI becomes a core layer of the economy, then AI infrastructure becomes critical infrastructure. The places that can support it may gain advantages. The companies that can secure capacity may move faster. The systems that can operate efficiently may scale better. The regions that cannot provide enough power, space, cooling, or connectivity may fall behind. The question is no longer only, who has the smartest model? The question becomes, who can keep the model running? Who can power it? Who can cool it? Who can supply the chips? Who can connect the systems? Who can build fast enough? Who can operate reliably enough? Who can turn intelligence into an industrial capability? That is why the hidden infrastructure behind AI matters. It changes the story from something abstract into something real. The AI revolution may feel like it is happening in the air. But it is being built on the ground. It is being built in data centers. It is being built in chip fabs. It is being built in substations, cables, cooling systems, server racks, and construction sites. It is being built by people who may never appear in the product demo, but whose work makes the demo possible. There is also a cultural illusion in the way AI is presented. The product demo often removes the machinery from the frame. It shows a clean interface, a fast result, and a sense of effortless intelligence. But effortlessness is the illusion created by scale. The smoother the experience becomes, the more infrastructure is usually hiding behind it. This is why a simple answer from an AI system can represent a complex chain of events. A request may touch networks, processors, storage systems, orchestration layers, monitoring systems, safety filters, power infrastructure, and cooling systems before it returns to the user as a few lines of text. The user sees seconds. The infrastructure carries the weight. And that weight is becoming a defining feature of the age. As AI moves from novelty to daily utility, the demand on the physical world grows with it. More tools, more users, more automation, more data, more inference, more training, and more reliability all push the hidden machine to expand. But expansion is never just a technical decision. It touches land, energy, water, construction, local communities, permitting, supply chains, and capital. Every new layer of intelligence must eventually ask permission from the physical world. That is the quiet truth behind the AI boom. The future may be digital in experience, but it is industrial in foundation. A society that wants more AI must build more than models. It must build the systems that make those models dependable. It must decide where the data centers go, how they are powered, how they are cooled, how their supply chains are secured, and how their benefits are balanced against their costs. The most important companies in the next phase may not be only the ones with the most impressive demos. They may be the ones that can coordinate research, hardware, energy, logistics, and operations into one functioning machine. Because intelligence at scale is not a single product. It is an ecosystem. And ecosystems fail when one invisible dependency breaks. If power is delayed, compute is delayed. If chips are delayed, training is delayed. If cooling fails, systems fail. If networks are weak, performance suffers. If construction slows, expansion slows. If trust breaks, adoption slows. That is why the hidden infrastructure is not background. It is the story. The AI revolution may be remembered for models, but it will be shaped by the machinery that allowed those models to grow. Behind every breakthrough is a facility. Behind every facility is a grid. Behind every grid is a political, economic, and physical reality. In the end, artificial intelligence is not only a breakthrough in software. It is a new demand placed on the physical world. And the future of AI may be decided by a simple truth most people overlook: the cloud has a body. It has weight. It has heat. It has limits. And the next phase of artificial intelligence will belong to those who can build, power, cool,